to repair, because during the repair actions, during the maintenance actions, obviously the system is stopped, is not working. How can we improve availability? We can improve availability by, for example, increasing the reliability of single components. That means increase the mean time between failures or the mean time between maintenances. It is not simple to increase the reliability of single components. It does not depend often on the company that perform maintenance, but it depends on the company that design components, the components. We can, the maintainability also can be improved, but also in this case, as we said earlier previously, it may depend on the component, on the company that design the component or the system. The availability can be also improved by using systems according to their design specifications. And in this case, it is an issue of the company using a system to ensure that the system is working in the correct conditions. If my car is designed to work in temperature between -15 and +50 degrees, and I go to Polo Nord, to the North Pole, I should expect that the availability of my car is reduced, because I am not using it according to its specifications. And we can also improve availability by, as said before, by reinforcing and training maintenance teams. In this case, we will reduce the mean time to repair. Okay, now we should start to talk about reliability. We will introduce some important aspects of reliability theory, obviously related to maintenance. What is reliability theory? First of all, it is the science that tries to predict, analyze, prevent, and reduce the failures over time. It is obviously strictly related to mathematics and statistics, and it is very important for maintenance because it can help in answering some important questions related, for example, to how much time the system will be available, which will be the total system availability, how failures can be prevented, which can be the life cycle cost for the system, and which are the most important risks related to the systems. Now, how can we obtain information about the reliability of a system? There are three possible ways. The first one is an analysis of historical data. This method uses historical information retrieved from the same system under analysis, used in similar environments and working conditions. So I can retrieve data from similar or from the same systems used in similar working condition if I don't have data related to my working conditions. I can retrieve the information by means of accelerated tests, for example, which uses information retrieved by a system submitted to hard working condition for a brief period. In this way, it is possible to estimate the mathematical law linking the system reliability and the working conditions. So in this case, I will not wait to retrieve data for years, because you should think that to obtain data about the reliability of system and components, if you want to obtain that data from the real working conditions by waiting the real failures during the working times, you probably should wait for years. Using accelerated tests instead allows to obtain such data in a very small time period, by operating some very hard tests on the components. Obviously, also the combinatorial reliability is a very important aspect to consider to estimate the reliability of a system. I don't know if you, in your study, if you already faced the reliability theory, but combinatorial reliability is very important, and we will see this, I think, also in the next lecture, because components have relationship. The components of a system have relationships among them. So it is possible that the failure of a component directly affects the correct working condition of the other components of the same system. So when we want, for example, to estimate the useful life or the reliability of a complex system, we should look at the relationship between the components of which the system is made. And each one of those components has its own reliability, and the combinatorial reliability theory tries to model the total reliability of the system, relying on the knowledge of the single component reliability and of the relationships among components. So these are the three main methods to obtain reliability information. But what is reliability? The reliability of a system can be defined as the probability that the system will perform the required function for a predetermined time under specific operative conditions. Now, we need four main features to consider, four main aspects to make the reliability concept operative. These aspects are the required function that we ask to our system, the operating conditions, the operating time, and the probability. Please note that in this figure, in which the reliability of a component, a system, is represented, the reliability function is a non-increasing function. So it cannot increase, but only decrease. What is the required function of a system? For example, for a car, the required function can be to complete a certain trip under any operating conditions, to complete a certain trip considering, for example, safety rules, or to complete a trip respecting the rules of the road. So in this case, we are specifying the required function of the system. The operating conditions concern instead the range of possible operating conditions in which a system can work. As I said before, a car can be designed to work in a temperature range between -15 and +50 and +15 degrees, or other operating conditions for the car can be to complete the ones related to the completion of a trip in different with different load conditions. For example, fully loaded or at maximum speed, only one person at maximum speed, and so on. Obviously, the reliability of the system changes according to the operating conditions. The operating time, as you can see also in the figure, is the time in which we consider a system reliable, and obviously, as you can see, the reliability decreases over time, starting from a value of 1, where this value indicates simply that a new system at time 0 is working, is starting to work. So at time 0, a system starts to work, and its reliability is equal to 1, or 100%, as you prefer. When we move over time, the reliability of the system decreases, and it will arrive for sure to 0 when the time tends to infinite. Obviously, the probability element that is the last one to consider when we talk about reliability is one of the most important, because we know that a failure will occur on a system. We know that in a certain point in time the system will fail. We can also know how that system will fail, but we don't know when it will happen. So in this case, we have to refer to the probability that a failure occurs. Okay, now we should give some other definition, but if you agree, we can have another little break of 5-10 minutes. What do you think, guys?
It's okay.
Okay, so see you in 5 or 10 minutes.
Okay.
Okay.
Okay, guys, are you there? Someone is still here? Okay.
Yes.
Okay, perfect. We have the last 35 minutes. Okay, well, the screen was already shared. Okay. You now cannot see my screen, right?
We see your screen.
You can see now the...
Yes.
Oh,
Not
nice.
the presentation.
Not the presentation.
The PowerPoint.
Yeah, okay, not in full screen.
Not in full screen.
Yeah, okay, okay. But okay, so I can set here. Okay, now you should be able to see in full screen, right?
Yes.
Perfect. So we introduced the concept of reliability, which is the main concept related to maintenance activities, and we will see why in few slides, but maybe in the next lessons. We also need to define other important aspects related to reliability theory. So we will give some definitions here. For example, we need to define what is the probability density function, and in particular, the failure probability density function. Generally, a probability density function, identified as a PDF, is the function used to specify the probability that a random variable falls within a specified range of values. According to this definition, the failure probability density function that we will identify as f of t here, small f of t, is the function for which the probability that a component fails at time t or in some infinitesimal neighborhood dt is f of t dt. Now, if you consider what we have said before, that a system when the time t tends to infinite has to fail, we can say that the integral between 0 and infinite of f of t in the t is equal to 1. This simply means that the system, that the probability that the system will fail at a certain time between 0 and infinite is 1. So we are sure that when t tends to infinite, there will be a failure. Okay. Now, we also need to define unreliability. We define reliability as the probability that the system performs as specified without interruption over an entire interval. The unreliability is exactly the opposite. In fact, it is indicated with great F, and it represents the probability that a system or a component will fail for a predetermined time under specific operative conditions. So, as opposite to reliability, unreliability, you can see here, is a non-decreasing function. You can see that it always increases, and it starts from 0 and is asymptotic to 1. So we know that the unreliability function will reach the value 1 when t tends to infinite. Thus, you can see that there is a relation between reliability and unreliability here. In particular, reliability is 1 minus unreliability. And obviously, unreliability, if we consider, for example, the failure probability density function generally for a lot of components can be interpreted, can be defined as a normal distribution, to have a normal distribution. In this case, obviously, unreliability represents the probability of failure. Reliability represents the probability of success of a component. And they can be, if, for example, we want to define the unreliability for the red part of the curve and the reliability for the green part of the curve, we should integrate between 0 and t for evaluating unreliability, t and infinite for evaluating reliability, the failure probability density function. Now, maybe this, I can try to do this on the electronic board. We can try to develop this together, also to make an example. So I will stop sharing the screen, and I will open another screen with the electronic board. I hope it's the first time, so it's new, so I had to try. But please let me share. Let me try. Okay. Okay, just a few moments. I am not able to switch the board on my other screen, and this is a problem because the board takes the entire screen. So when I have the board open, I cannot do anything. Oh, maybe we can do this. Let's try. Let's try to share. Okay, can you see the board now? A white page.
Yes.
Okay, perfectly. So let me try to. I also do. Okay, it seems to work. Okay, so we were talking about the failure probability in a specified interval. For example, if we are interested in calculating the failure probability within a specified interval, seems to doesn't want to work. Just a few seconds, please. to this one. Just let me check now. No, it doesn't work. Now, okay, now it seems to work. Can you see the board now?
Yes.
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 No,
Not now, because now you see my desktop.
exactly.
Okay. Let's try again. Not this. This one. Okay, now you should be able to see the board. Let's try again. Okay, we were trying to evaluate the failure probability within a specific interval. That is, for example, okay, T1, T2. Okay. For what we said about reliability and unreliability, we can say that it is equal, this probability failure is equal to f of T2 minus f of T1, and it is also equal to yes, 1 minus R of T2 it is very difficult to use the electronic board, minus 1 minus R of T1, because you should remember that great F is 1 minus R. Okay, so this is also equal to R of T1 minus R of T2, because 1 minus 1 here, 1 minus 1 is 0, and this is minus minus is plus, so RT1 minus RT2. Now, if we are interested in calculating the failure probability within a specific interval, a different interval, for example, T2 or T2, T3, let's say that this new period is T2, T3, okay? But knowing that the system has already passed T1, so he is already existing from T1, okay? In the first case, in this case, we want to evaluate the probability that a system failed, for example, in a specific interval T1, T2, supposing that it was starting to work from time 0. Now we want to evaluate the probability that the system fails between a time interval, in a range of the time interval T2, T3, knowing that it already worked for T1. Okay, so we want to, in this case, we want to estimate the probability that the, let's call great T, the time in which we expect the failure. So we want to calculate the probability that great T falls within T2 and T3, knowing that this symbol, I don't know how it is in English. In Italian is dato che. I will call since, not knowing that, T will pass T1. Great T is greater than a certain time interval T1. In this case, we can say that this probability will simply be equal to this quantity, f of T3 minus f of T2 divided by R of T1, or that is equal R of T2 minus R of T3 divided R of T1. Now I have a question for you. According to your opinion, suppose that, for example, T1, in this case, we have the same time interval, T2 and T3, and T2 and T3. According to you, the probability that the system fails is greater in this case or in this case? Remember that the difference here is that here we know that the system already arrived to T1. Here, the system starts to work from zero. So how do you think will be greater the probability of failure, or talk about, for example, the reliability? Which system will have a greater reliability? The system that is working already T1 and in which we are trying to evaluate the failure from T2 to T3, or the other one that is working from zero? This is not a very simple question, also because it is not very simple to understand. Okay, I will try to ask, but by means of a curve. So let's think to this example. Okay, we have the reliability curve that is something like this. Now here, in which here we have reliability, and here we have time. Okay, the reliability curve, as we said, starts from here, that is 1, and as an evolution like this one. Okay, this is asymptotic to 0. Now, suppose that, for example, T1 to T1, the system had a reliability. So, for example, this is T1, this is T2, and this is T3. Okay, so T1, R of T1 is equal to what to say, 0.5. R of T2 is equal to 0.3, and R of T3 is equal to 0.2. Now, if we want to, if we look here and we want to estimate the in the first case the probability that the system fails, or the reliability that the system has between, in this case, suppose that it is T2 and T3, supposing that the system is new and now is starting to work, we simply should apply this formula, this equation, no? So RT1 minus RT2 in this case RT2 minus RT3, supposing that it is starting to work now. Now it is the time 0. So the probability that the system is still working between T2 and T3, that is reliability, RT2 T3, is simply RT2 minus RT3, that is 0.1. We have a 10% probability that the system will be still working between T2 and T3. Okay? What we want to know now is which is probability of being working, so its reliability, knowing always between T2 and T3, knowing that it is already arrived to T1. In this case, we should apply this formula. So we can write it here, for example. We have R T2 T3 knowing that it is arrived to T1 equal to 0.3 minus 0.2 divided by 0.5. And this is equal to 0.1 divided 0.5, that is equal to 0.2. So you can note that when we try to calculate the reliability or the probability of failure of the system, assuming that the system is now starting to work, that probability, that reliability is simply the difference between the reliability at the starting period we are considering minus the reliability at the ending period we are considering. But when we try to evaluate the reliability, considering instead the fact that the system is already arrived, is already passed for another instant of time, in that case, that reliability increase. In fact, in this case, the reliability is greater than in this case. That's why, obviously, if we know that a certain item is already arrived to live a certain period of life, so it is not failed before, in this case, for example, T1, the probability that it will arrive in good condition between T2 and T3 will be greater than the case in which we are now starting to work with a new component. I think this concept is not very is simple, but if you have any doubts or something, please stop me and ask me for questions if you have. It is an important concept for us. Okay, if you have no questions, I think we can go to the PowerPoint again. Okay, please just let me. Okay, let me share the PowerPoint. Can you see the PowerPoint?
Yes.
Okay, perfect. So what I just explained is what is written here, but why is it important? It is important because we have to define the failure rate of the system, of a component of an item of a system. But since it is we have only 10 minutes, maybe we can focus on the failure rate next time, and now we can simply read this slide and try to do an exercise together, because we are looking to reliability and unreliability functions as continuous functions over time, but we can we often deal with discrete elements. So we have 3 cars, 4 components, and so on. When we refer to discrete elements, or also to discrete time interval, the reliability function can be interpreted as the fraction of the system population that still works in the considered time interval, by referring to the initial population at time t equal to 0. So, referring to a specific period, to a specific instant of time, t1, if we want to evaluate the reliability of for a population of components, for example, we should simply do the ratio between the population still working in T1 and the original population at time equal to 0, at time t equal to 0. Obviously, the unreliability is 1 minus the reliability. So, how can it be interpreted? Unreliability can be interpreted as the fraction of the system's population that failed within the considered interval T1, referring to the initial population at time t equal to 0. Now, imagine to have, okay, not this one, this example, okay? In which, for example, you experience, sorry, I forgot to change here in English. This is the number of failure, okay? Imagine that you have 6 time periods from 0 to 1, 1 to 2, 2 to 3, and so on. And you want to estimate reliability and unreliability. For what we said before, reliability is the population still working, the ratio between the population still working divided by the initial population. Why? While the F is the ratio between the population failed related to the initial population divided by the initial population. So we experienced 2 failures in the 0-1 interval. And as you can see, the reliability of the system, considering a time interval from 0 to 1, we have 16 total items. Since only 2 failed, reliability is the number of systems still working, that is 14, divided by the total initial number. So the reliability of this system in a time interval 0-1 is 14 on 16. The unreliability is simply 1 minus the reliability, but you can also look at unreliability as the number of systems failed on the total number of the population. So reliability is 14 on 16, unreliability is 2 on 16, because only 2 failed. Okay? In your opinion, which are the reliability and unreliability of this system, for example, in the period 2 that goes from 2 to 3? With this question, I think we will close the lecture of today. And R taxi, because we always need to look at the still working components on the total population for the reliability and the failed components for on the total population for great F of t. So, as you correctly answer, in the period 2-3, to calculate the reliability, we simply need to know which are the components still working, that are 7, these ones, while the failed ones are 9, 4 plus 3 plus 2, 4 in the period 2-3, plus 3 in the period 1-2, plus 2 in the period from 0 to 1. Continuing, as you can see, reliability and unreliability, as you can see, reliability is a non-increasing function because we started from 16 on 16, okay, from 1 at time 0. 2 failed and 14 and 14 left. Then 3 failed and 11 left. 4 failed and 7 left, and so on. So reliability still decrease over time, always decrease over time, while unreliability is exactly the opposite. It starts from 0 at time 0. Then we count the number of failed components. So we have 2 plus 3, 5, plus 4, 9, plus 3, 12, plus 3, 15, plus 1, 16. And so I think I have some image. Okay, this is not this one. In which I should have part of both reliability and unreliability, maybe at the end of the this one. So you can see this is referred to another thing that we will see in the next lecture, but you can see that reliability and unreliability has two opposite tendencies. Reliability is non-increasing function, while unreliability is a never increasing function. So it always increases. Okay, we have another minute and a half, so I think we can stop here. If you have any question, please ask me. I don't know. Okay. If you have no questions, guys, I think we can leave the lesson. I don't know if Valentina has something to say to the guys.
No, I think that it's all, and we'll see Friday at 9. Is okay for you?
Yes.
Yes. With Professor Pianese, the lesson started at 11 or not? Okay, I don't have the camera. Okay, so I think that it's good. So you'll have 20 minutes as break. Okay.
Okay, Valentina, can I share this material with the guys on the? Okay.
Yeah, on the file section of the
perfectly.
file folder.
Maybe I can share also the lecture. I will start the next one.
Probably, yes.
Okay, so I should not need to divide. Perfect. Okay, thank you.
Okay.
Bye bye.
Ragazzi.
Bye bye everyone.
Bye.
Thank you so much.
Comunque non avete